Welcome to my channel for technical discussion. Today I will discuss about relative humidity part 2. Topics of discussion: mass of water vapor per kg of dry air, change in relative humidity due to change in pressure, and change in relative humidity due to change in temperature. Equation of state for water vapor and dry air. So first equation is for water vapor. So we can write PV into V is equal to a small mv upon capital MV into R into T. Second equation for dry air, which is written as PD into V is equal to MD upon capital MD into R into T. And third equation is total pressure P is equal to PD plus PV, where PV is the pressure of water vapor in Pascal absolute, PD is a pressure of dry air in Pascal absolute, a small mv is a mass of water vapor in kg, md is a mass of dry air in kg, capital MB is a molecular weight of water, which is 18.015, capital MD is a molecular weight of dry air, which is 28.965 kg per kilomole. P is the total pressure in Pascal absolute, V is the total volume in cubic meter, and T is the temperature in degree Kelvin. R is a universal gas constant. From equation 1 is divided by equation 2. So by division of 1 by 2, you will see PV upon PD is equal to a small mb upon a small md into capital MD upon capital MB. By rearranging, a small mb upon a small md is equal to capital MB by capital MD into PV upon PD. From equation 3, we can write PD is equal to capital P, means total pressure, minus PV. So we can write a small mb upon a small md is equal to capital MB upon capital MD into PV upon P minus PV. Putting the mass of dry air, md is 1 kg, we can write mass of water vapor per kg of dry air is mb is equal to capital MB upon capital MD into PV upon PV upon P minus PV. The mass of water vapor, by putting the molecular weight 18.015 for water and 28.96 for dry air into PV upon P minus PV. This is equation 4, and just division of this value, we can write now mass of water vapor per kg of dry air MB is equal to 0.622 into PV upon P minus PV. So equation 4 and 5 here should be equal. Equation 4 and 5 can be used for calculation of mass of water vapor per kg of dry air. Now we'll see what is change in relative humidity due to change in the pressure. When the pressure increases, volume decreases, and that leads to be less space for water vapor, and so relative humidity increases, and vice versa. Take the case of this is unsaturated condition, and if pressure increases, the volume decreases. So space between dry air has now reduced, and that is why the relative humidity increases. We'll see with this example. Condition 1, P is 1.013 bar absolute, T is 30 degrees Celsius, R is 70%. Condition 2, now P has increased, it is now 1.2 bar absolute, and temperature remains same as previous case, that is 30 degrees Celsius. Now we have to see what is the value of RH now. The mass of water vapor remains same in both the condition. So now we'll see the calculation. Pressure, case number 1, pressure is, now we have to convert in Pascal, so it is 101.3, temperature is 30 degree, relative humidity is 70%. So saturated water vapor pressure can be calculated based on temperature, which is 4.2443 kilopascal. So vapor pressure can be calculated now. RH multiplied this will be 2.97099. Now mass of water vapor per kg of dry can be calculated using this equation, which is coming out 0.1879. This is case 1. Now case 2 also, P has now increased, it is now 120 kilopascal. Temperature is the same, 30 degrees Celsius. Now this equation, now we have to calculate PV, where MB is the same as case number 1. So MB value is taking from here and P is here 120. So PV is calculated, which is now 3.51944. Buck equation, saturated water vapor pressure is the same because temperature is the same. Previous also 4.2443, it is also 3. Now division of this will give the RH. So relative humidity is PB upon PVS into 100. It is coming around 82.92. So see, by increasing the pressure, relative humidity also increased. Now we'll see the relative humidity change due to change in the temperature. When temperature increases, volume increases, and that leads to more space for water vapor, and so relative humidity decreases, and vice versa. This is case of unsaturated condition. Now temperature has increased, so now more space is available, and that is why relative humidity decreases. We'll see in the next slide how with the calculation. Condition 1, pressure is 1.013 bar absolute, temperature is 30 degrees Celsius, RH is 70%. Condition 2, pressure remains same, 1.013 bar absolute. Now temperature has increased, now it is 50 degrees Celsius, and we have to see what is the value of RH. Please note that in both the case again, mass of water vapor remains same because it is not condensing. So in both case, mass of water vapor will be same. So pressure 101.3 kilopascal, temperature this, relative humidity is 70%. So saturated water vapor pressure is 4.2443 using this equation. Vapor pressure will be 2.9709. Just multiply RH with this, we get the vapor pressure, and then mass of water vapor per kg of dry is calculated using this equation, where P is this and PV is this. So we will get 0.1879. Again, now pressure in the second case is same, temperature is now increased. So vapor pressure of water, again you have to use the same equation. MB will be same, so you have to take this MB value here, and P you have to take this. So PV will be same because P total pressure is same, M is also same, and so that is why PV is the same as before. You see the PV is 2.97, here is also 2.97. However, saturated vapor pressure has increased because temperature has increased. So earlier it was only 4.2, now it is 12.34. And that is why relative humidity is PV upon PVS, which is reduced this by this into 100. And that's why you see relative humidity is now only 24.0%. With this, I have finished my lecture. Hope you will like this discussion. If you have not subscribed my channel, please subscribe it, like it and share it. See you in the next discussion. Till then, bye bye. Thank you.